Okay, this is going to be the review for our midterm exam in algorithms class. So it's going to kind of go over some highlights here, and this will be a lot of detail. I'll put a forum out there if you have questions, and I don't mind, doing a video for answering a question or getting on Zoom or whatever you think that you need. Just let me know. Again, we'll have our normal review or our normal office hours on Thursday, and we'll go over any questions you have then. And the test itself will be available starting on Friday, going through Sunday at, I don't really care what time you do it. So I guess until Monday morning, it'll be okay. But you'll have 2 hours, but I'm planning it like it's a 1 hour exam. So that should give you some flexibility. Okay. So when we go through the chapters here, I think that we can probably go through mostly through the table of contents. We can talk about stuff. Okay. The first chapter is a lot of just background information. Okay. So some of these things could come into a question. There are going to be some questions that are going to be half-page essay type questions. You've probably had those with me before to explain the concepts. So you should know what an algorithm is, what it does, what we're trying to do, talk about the different design techniques, talk about how our algorithms have to be unambiguous. We have to say what domain of problems they work for, all that stuff. Okay. So, and then the different problem types. I'm not sure there'd be a question about it, although there could be, but it's more we're going to use those in the other kinds of problems that we talk about. Okay. And then on down, that went exactly where I didn't want to go. So let's go back. Almost, we're getting there. So we then get into section 1.4 on the fundamental data structures. And again, you guys just had data structure classes. So hopefully, as we've been using them, you understand that the linear data structures such as arrays, graphs, trees, sets, dictionaries. We haven't got to sets or dictionaries yet, I don't think. Oh yeah, we have. On the closest point problem talks about a set of points. Okay. So yeah, those are more background knowledge than something I'm going to ask you directly. Okay. So chapter 2 is the most ambitious, that's the word, not ambiguous, the most ambitious mathematical chapter that we have in this entire course. So I'm not looking for a ton of detail there. I want you to understand what's going on. I want you to understand how we measure the input size and how we get the orders of growth based on the number of input size that we have. To know what a best case, worst case, and average case efficiencies look like, to know which problems are likely to have those. Okay. And then as far as the notations, the big O is the one we really care about. So big O is important to know. I won't ask you the other two. Okay. There's some properties we talk about there that are useful. Okay. Section 2.3 on the non-recursive algorithms with the summations. I mean, be ready for that. I'm probably not going to give you a summation problem, but you should understand how that works. Okay. The other stuff there with recursive algorithms, that's more math than I want to make you do. Okay. So chapter 3 starts our search through the different techniques we can use to solve problems. Okay. And knowing each of these, what they do, being able to do some examples, compare and contrast the types, those are very likely things you're going to see on the exam. Okay. So with the brute force, again, you hit it with a hammer until it's dead, kind of an idea. We get the selection sort and the bubble sort. Those are slightly different versions. Selection sort's not the worst thing in the world. Bubble sort kind of is the worst thing in the world. The reason being that you're switching everything every time. Okay. So the selection sort works basically, you go through and find the biggest in a set of numbers, put it at the end, and then do that again. The bubble sort, you're switching neighbors all the time, all the way through. So at the end of one run, you're going to have the same result. They have the biggest number at the end, but the bubble sort does a whole lot more switches to get there. Okay. Then we talked about the idea of sequential search and brute force string matching. Both of those don't require anything fancy. We're going to get to string searches later that are a little better, but you start at the beginning and keep going till you find it. Okay. And then we have our closest pair and convex hull problems. We have those by brute force. We also have them by divide and conquer. So I like these problems. You're likely to see one or the other of them on the exam in some version. Either the convex hull or the traveling, or sorry, the convex hull, the closest pair problem, done either by brute force or by divide and conquer, or both. Either ask you to write the algorithm, solve a problem using the algorithm, write the pseudocode, or just write a generic description, one of those kinds of things, okay? And then we have the exhaustive search with the problems that we're going to talk about later that really don't have good solutions, like the traveling salesman problem or the knapsack problem or the assignment problem. With those, you just have to try every possibility until you find which one's best, okay? The depth first search and breadth first search, you should be familiar with those terms. Again, they're a brute force way to go through a tree or some other kind of graph structure. The depth first, you're looking to get as far away from the root at every time, where the breadth first, you're covering everything connected to the root before you move on, okay? So we then went on to the idea of decrease and conquer, okay? Where you're going to, remember there are three options there. You can either reduce it by one, okay, which is what a brute force tends to do, like a selection sort, reduces it by one. You could reduce it by about half, which is what the divide and conquer, which we're going to do next later, does. And then you can also do a variable size decrease, okay? And they give you some problems there that you don't always know how much you're going to reduce by, okay? So this had the insertion sort, which is a little bit better sort, okay? It also gave us the idea of topological sorting. That's the one where you have the example was the class prerequisites. So it's a way you either go as far as you can and remove that destination node, and then you go backwards when you're done and reverse it, or you look at which nodes are sources and have nothing coming into them, just something going out, and delete those, okay? And both of those are fair games, okay, fair game. The algorithms for generating combinatorial objects and the permutations and subsets. Yeah, I mean, you may see those. Those are certainly okay. Binary search is something I could ask you about on into 4.4. I will probably not ask you a fake coin problem. If so, it'll be a pretty straightforward one. We won't do Russian peasant multiplication or the Josephus problem, either one, okay? And on the variable size decrease algorithms, there's not really, let's see, do we get if we get the Lamudo, I'm not sure if Lamudo comes in there or not. If Lamudo's in that section, then on the partitioning, that may be in the computing immediate and the selection problem. If so, then that's worth knowing. The rest of that stuff is not something that I'm going to ask you about. Okay, so that's kind of where we're at on that section. So that's not one of the more important ones. Sorry, I had to temporarily distracted. I had to move my seat around. So the Lamudo is important, but nothing else in that section is anything that I'm going to ask you about. Okay. I mean, I guess the binary search tree, we're going to see that again, so that's not a bad idea. Okay. Chapter 5 gets some big stuff. Okay. Merge sort, quick sort. So you should be familiar with both of those. Those are both the go-to sorts for computer scientists. Okay. So know how they work, know their efficiency class, all that stuff, be able to do an algorithm with them, be able to do an example on some real data, okay? Know why you would do one or the other. Remember that merge sort has a better average efficiency, but the quick sort, depending on how you choose your partitioning, can be better in some cases, okay? Be easier to implement, okay? So we then talked about binary search tree traversals. That's the pre-order, in-order, and post-order. Those are pretty quick problems to do, so I may give you an example of that. On the large integer and Strauss's multiplication, skip all that for the exam. Okay, so nothing in 5.4 will I ask you about. Okay, 5.5, I'm interested in both of those, the closest pair and the convex hull problems done with the divide and conquer. Okay, so remember with the closest pair, you start by dividing up things. You find the median line between the two extremes of the points, divide it into two groups, and then you find the closest in each group, and then check it against those that are in that median to make sure that they're not any shorter, okay? And then with the convex hull problem, it's where you find the two extreme points in terms of their horizontal values, and you then divide the points into those above that and those below, upper hull, lower hull, do those individually. You then find the point for each of the sub-hulls. So for the upper hull, whichever point is furthest away from the line that goes between those 2 points, you add that as a triangle, and you check to see if all the points are inside of that or not. Okay, so both of those are worth knowing for sure. Okay, and then we got to the last chapter was on the transform and conquer. Okay, the pre-sorting is a worthwhile thing. Remember, with the pre-sorting, it's going to take you at best n log n. Okay, so any algorithm that has a big O of n or less. Okay, so if it's constant or n or log n, it cannot be improved by doing a sort. In fact, if it's an n log n already, then to do that twice, basically, to do an n log n to sort it and then do an n log n to implement it on the sorted list would not be worthwhile. Okay, so it's really only anything that it is n squared or greater. Would it make any sense to try the pre-sorting? Okay. On the Gaussian elimination, the only thing I would ask you would be to solve a system of equation, not the LU decomposition, not the matrix inverse, not the determinant. Okay. Balanced search trees. I could ask a quick question on that, whether something is a tree or not and what the balance factor is. Remember, the balance factor is the for every node, and you start with the furthest nodes out, the leaf nodes. It's the length of the left subtree minus the length of the right subtree. Okay. And it's a balanced tree if that factor is never more, if it's either a 0, a -1, or a 1. Okay. And the other thing there with the 2, 3 trees, probably not going to ask you about. No, I will say, I'll be clear, will not ask you about. Okay. The next set talks about heaps and heap sort. Heaps are very interesting. They're kind of like a partition. The heap has the characteristics that it's a essentially complete binary tree, and that's the shape that we have to have. That's one of the factors you need. And the other is the parental dominance, which means for every node, the node is bigger than all of its children. Okay. It doesn't say anything about the siblings, so it's not a binary search tree. It doesn't have any of that structure. Okay. But we use that in the heap sort by if you turn a list of numbers into a heap, either with the bottom up, which is where you throw them into a general binary tree, and then start at the bottom left and start flipping them around to see which ones are correct. No, sorry, bottom right, I think. Check the book, it would know. I think it's bottom right. I'm not sure it matters if you're on the right level. Until you get into a heap, and then you know that the root of the heap is the biggest element. So you pull it out and then reheapify and start again. Okay, so that's the heap and the heap sort. Those are important. Okay. Horner's rules of binary exponentiation didn't cover, don't worry about it. And nothing from 6.6 I'm not going to ask you about. Okay. So that's kind of an overview of what's going on. I'll try to make sure, it looks like I skipped some of the homework solutions. I've created a homework solution page for every single one of our homework assignments except the last one. I may even have for the last one, but I'm not sure that I've put all those out there. So I will take a look to see, to make sure. Okay. The test itself will be open book, open note, open internet. All I don't want you to do is phone a friend or work together or any of that stuff. Okay, it should be your own work. Okay. So again, if there are questions, we'll have our meeting on Thursday. If you want to meet some other time just to run over some stuff, let me know. I'm not available all the time, but I am available a lot. So hopefully we can work out a time if you need to do that. Okay. So if you have questions, make sure that you let me know. If not, I will see at least some of you on Thursday.